Let's look at some examples, and then the surprise fact at the end will follow. So this is called the Sierpinski triangle, and you can immediately, due to this coloring, fortunate coloring, by the way, all these pictures I've taken from Wikipedia. I've tried to check that they're in public domain, but even if they are not, I'm not claiming that I made any of them. You can immediately tell which pictures are mine. Okay, so here you can tell that S1, for example, is the map that takes this triangle into the yellow triangle. And for that to happen, so S of x, so 1 goes to 1/2. Here, this vector is divided into 1/2. So this point goes here, this point goes here, and you can hope that the rest works. So this will be that. And the others are just shifts of that. So S2 of x will be 1/2 of x. If I want to get the blue one, then I add 1/2 and 0. And S3 is just similar. You can again check that the open set condition is satisfied if you take the interior of the original triangle. You can easily check that the open set condition is satisfied. From all of this, we see that the self-similar set K will have dimension given by log of, well, we have 3 of them, and each one is 1/2 scaling. So that becomes the Hausdorff dimension. It's just an amazing, quick way of calculating the Hausdorff dimension. Of course, all due to beautiful theorems due to Hutchinson. Let's first look at this easier one. So maybe you can pause and think about whether this is self-similar, what are the similitudes? And if you have resisted doing that, the first one will be to take this full cube, so it's solid, everything is inside included, and then you map it to just this one. So this becomes that. And if this is 1, then this will be 1/3, and here also 1/3. So S1 will be 1/3 of x. And then this will be, if you count counterclockwise, will be 1/3 of x plus 1/3 and 0, and so on. So this will be S2, S3 maps the full square here, and here, 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 and here, and we don't map anything here, so it's just going to be void. If again you take O to be the interior of 0, 1 to power, well, now I made it an interior, so if you take the open set to be 0, 1 to power n open cube, then open set condition is satisfied. Very easy. So we do get a self-similar set whose Hausdorff dimension then will be, you have 8 similitudes, and each one is division by 1/3. So 1/r, 1/1/3 is 3. So amazing. So, and this is some number bigger than 1 but less than 2. This is called Sierpinski carpet for apparent reasons. Okay, let's go back to this one. So this is Von Koch snowflake. Some facts about this is that it's a continuous image of 0, 1. That's why they also call it a curve. So it's a continuous curve, but it's not a rectifiable curve. Hausdorff dimension, as we will soon see, is strictly bigger than 1, so no part of it, except for singletons, is rectifiable, which would mean that it has finite length. The area inside it is actually finite. Well, because you can take a much larger box and that's inside it. So any 2 points you take on this, there is infinite length traveling between them. So there isn't finite length. You cannot basically move off with finite speed. But how is this constructed? And that I intentionally left for as the last example, because it's not so easy to see. So I start the construction and I'll leave the open set condition as an exercise. You can start with a unit line segment. And in the next step, and I'm thinking of this as sitting in R2. What you will do is that you want to end up with this shape. So you want to replace one line segment with 4 line segments. And can you do this with similitudes? I think so. The first one, so take this to be your K. It's a compact set. And S1 of K is going to be this set, so S1 of X should be the map. So if this is going to be broken into 4 equal parts, so that has to be 1/4 of X. And the image is this, so 0 goes to 0. Now we need to get this part, which is S2 of K. We see that the scaling is 1/4. Scaled 1/4. But then there's also rotation. Then rotate 45 degrees. And that is a similitude because, well, after rotation, the distances don't change. Then there's this easy part, the shift part. So this will be, if rotation by 45 degrees is like, let's write it with this, is this operation. You rotate, of course, you can first rotate and then shrink, and then you add 1/4 and 0, because that's where you want 0 to end up. And that will be it. And then S3, you can now guess, and S4 is again an easy one because that will be 1/4 of X plus 3/4 0. Okay, so you do this, and if you've seen the snowflake before, you just repeat. And repeating, if you can do it just kind of intuitively, but the better way here to really follow the theory will be to apply S1, S2, and S3 and S4 to this shape. Like take this to be your second iteration. Maybe let's say this is K0 and then this is K1. So apply these to K1 and honestly, without cheating, calculate, and you must see, again, this will be 0. So this segment will be replaced by 4. That segment will be replaced by 4. And that should get you back to here again, 3/4, and then back back to 1 again. And this will be K2, which will be, well, I must say here K1 is S1 of K0 union all of the others S4 of K0. And K2 will be S1 of K1 union S4 of K1. And then you repeat this until infinity. That's how you have the snowflake. So snowflake will be the unique compact set which will ultimately, so these ki's will converge to the snowflake. And snowflake is the unique invariant set under this operation. Okay. What I wanted to leave an exercise. This time around, it's a bit difficult. Check the open set condition for the one cock snowflake. Well, technically, it's checking it for the similitude S1 to S4, not the snowflake. According to theory, we start with checking the open set condition so that then we can say the invariant set will be self-similar. But once you do that, you can apply the theorem to see that the dimension will be log of 4. So you have 4 similitudes. One, two, three, 4. Okay. And then each time you divide them. Okay. The ratios are 1/3 because if they were 1/4, I would get 1. Okay, here's where I messed up. So just looking at this picture, the line segment has been divided into 3 parts. So these are, sorry about that, 1/3. So probably this changes. Yeah, so the ratios, sorry about that, are 1/3. Yes, so you take the middle 1/3 and you replace it by this. Okay. So you see this effectiveness and beauty of the whole theory. Now, what was the surprise part? Okay, this theorem that said to every collection of similitudes, there exists a unique invariant set, i.e. a set K such that it's closed under this operation, is proved by existence of fixed points for contraction maps on complete metric spaces. Yeah, the fixed point theorem, the famous abstract fixed point theorem, that if you have a complete metric space and some map between itself that is contraction, that is shrinking the distances, there is a unique fixed point. How this is done is by looking at, so the space here we're talking about is the space of all non-empty compact sets in Rn. And then to that you can assign a distance, which is called Gromov-Hausdorff distance. If you give me two compact subsets, I can tell them how far they are from one another. And then you prove that this metric space is a complete metric space. Then taking a set K to this one, is a self-map. So if this is space X, so this is a map from X into X again. Now the fact that each SI is a similitude and shrinks the distances can be used to quite easily prove that this map, what should we call it, T, maybe. So T is a contraction. And from that, because it's complete and this is contraction, there exists a unique fixed point of T. And what is a fixed point? It's exactly this condition. Okay, but then there is another remarkable fact about this fixed point theory, is saying that starting with any point and applying the map T, so if you start with any X and then, so that's how you actually prove the fixed point theorem in this context, that you just keep applying T again and again, and you prove that this converges to the fixed point. So what is some X in X? That means any compact set, so because elements of this X are compact subsets, any compact non-empty set in Rn. So if this everything is true, if abstract fixed point stuff are really true, this is saying that if you start with any compact non-empty set and you apply this procedure, you will converge, and here convergence is this Gromov-Hausdorff sense, to the invariant set, to the self-similar set, if you have this additional open set condition. And that is just amazing. By the way, this is something that I've been doing without telling you, intuitively, and every time we say, okay, and then repeat this process and you will converge, you will lead, you will end up with the final counter set or something. What we mean by you will end up with, or you will get close to, is exactly convergence in this Gromov-Hausdorff distance. So I've been applying this in a cheating way above. So that's how in many of these examples I started with some unit cube and then applied these SIs and then repeated. I did it in this snowflake construction. I start with K0 and then I apply this map. You see, to K0 I get K1 and then I apply this. This is applying this capital T. Then I get with K2 and so on. And I'm saying that in the limit you will approach the snowflake, and this is Gromov-Hausdorff metric approaching or convergence. Okay, so when I see such a result, what I always do is try to break it. I know that the theorem is most likely correct because it's in an honorable book by an honorable mathematician. The reason I'm looking at trying to break it or looking for counterexample is just to appreciate how deep and amazing it is. So any compact set, when someone tells me, and non-empty, I look at a singleton, just 1 point. Then are you saying that if in all of these previous constructions, if I just started with just 1 point of my choice anywhere, then this repeating iterative process would lead me to the self-similar sets that always that occurred at the end? And that looks kind of remarkable, at least to me. So how does that happen? How can you construct such apparently complex self-similar sets just out of a singleton? And that's why I try to do it with again an example. Let's see if we can construct the four-corner counter set just for simplicity. If I start with just a singleton, and to just keep my calculations maybe doable, I keep it to the origin. I don't want to challenge also myself in calculations. So we call that S1, and we had four similitudes, S2, S3, and S4 are 1/4 of x plus the shift, which is different for each one. Okay, so I'm gonna draw this square each time, but at this point it's not part of my set. Maybe I can use, okay. And I'm applying this t, which is saying that I apply S1 to the set, and then I apply S2 to the set, and then I take union. Okay, so this is S1 union S4 of whatever I start with. So let's apply this several times to a single point and see if we honestly are getting anywhere close to the four corner set. So this is my original set, K0. This is my original point I start iterations with, and I want to iterate and see if I converge to the four corner set. So what is T of that point? Well, S1 of that point is just that. S2 of that point, remember S2 is again shrink by 1/4 and then shift origin to this point. So it's here, S3 is here, and S4 is here, right? So if there were the full boxes were mapping to here, but now I'm not starting with the full box. Okay, now one point I started with, and when I apply T, I get a new compact set, K1, which is the 4 points. I apply that again, so that means I will shrink everything by 1/4. So this one, 0 again remains 0, so this divided by 1/4 will go, okay, this is 3, 4, so this will go somewhere here, I think, and this will be here, and this will be here. It will remain a square because, well, shrinking by 1/4 keeps a square square. And then the others will be copies of that. The thing I'm not sure about is whether, yeah, it probably will reach this upper thing. Another thing is really just to use my app to shrink things. So that will be this K2, which is T of previous one. And once I repeat, then I will have these dots. So now we'll have 4 times 4, 16. So this one, for example, will become like this, and then this, and then this. Okay, and then I will have copies of it here and there. So here. So it seems like actually we're getting there. We're increasing the number of points, and we also are getting them in the right places. Okay, so, and I'm losing some accuracy, of course, due to my very strange square. Okay, let me then sheet here and then, okay, something like that. And this is now K3, which is T of K2. And I think, at least I convinced myself that this really is going to converge to the counter set. A fun one that I recommend is start with 1/2 and 0 on KZ. Okay, and then construct the Van Gogh set. That one is even like funnier to draw and a bit tricky, so it's kind of a nice puzzle. Okay, so that brings us to the end of a quite comprehensive study of self-similar sets. If you have any questions, put them in the comments, and well, see you in the next video.